We want to look at what happens if different mass cars, and we're still in the inelastic region, so we have Velcro here. I want to look at what happens if I have a heavy car with lots of mass on it, and it's sitting at rest, and I'm going to just have this car come in and fly and hit it. So you can imagine, um, if you wanted to look at the extreme case, you have your car. What's going to happen with your car if your car is parked on the road and you, a small person, come in and crash into your car? What will happen? So let's look at that real quick. So that one's going to be at rest, and I'm going to crash the light car into the big car, and we have the collision. Let's look at the physics and the momentum transfer for this case. We've got two cars. One of them is really heavy, so let's make this light one 2 kilograms, and let's make this one 8 kilograms. Let's say that this guy flies in with a velocity of 10 meters per second, moving to the right, and let's have this one stop at rest, so this matches what we just saw before the collision. After the collision, we have 2 kilograms and 8 kilograms all squished together. So we have a 10 kilogram total car, and we want to know what's the velocity. Momentum transfer. Momentum is mass times velocity plus mass times velocity. 2 kilograms times 10 meters per second plus 8 kilograms times 0 meters per second. And we end up with 20 kilogram meters per second. Over here, momentum is mass times velocity, so it's 2 plus 8 kilograms times some unknown velocity, so we have 10 kilograms times that velocity. Momentum is conserved for the whole system, so those two are equal. We end up with 20 kilograms meters per second equals 10 kilograms times some unknown velocity. We can solve that easily and say velocity is equal to 2 meters per second. Notice what happens. Again, we'll interpret. The 2 kilogram guy slowed down. It was going 10, now it's going 2. The 8 kilogram guy, it was not moving, and now it's sped up. But let's look at relativity. How much did it? This lightweight guy went from 10 to 2. It lost almost all of its velocity. The big guy went from 0 to 2. It didn't change very much at all, so the change in velocity or the acceleration was small for this guy. The change in velocity or the acceleration was very big for this guy. We can look at that acceleration change. So we're looking and we're saying as a result of this collision, this guy went from 10 to 2, big change in velocity, big acceleration. This guy went from 0 to 2, small change in velocity, small acceleration. How can they have a different acceleration if we think that they're going to have the same force on them? Because Newton's third law says 2 pushes on 8, 8 pushes on 2. Those forces are in opposite directions but the same size. Let's look at impulse and forces. If I look at just this guy, just the 2 kilogram box, how much momentum does the 2 kilogram box have? 2 kilogram box has 2 times 10 or 20 kilogram meters per second of momentum before the collision. Afterwards, if I look at just the 2 kilogram box, all by himself, 2 kilogram box has 2 kilograms times 2 meters per second, because that's my new velocity, right? So afterwards, it has 4 kilogram meters per second worth of momentum. Look at what happened to the 2 kilogram box. It had 20 kilogram meters per second, and now it has 4. The change in momentum, the impulse for the 2 kilogram box, it went from 20 to 4. It lost 16 kilogram meters per second of momentum. And you might say, well, wait a minute, I thought momentum was conserved. But it looks like if I'm looking only at this box, the 2 kilogram box, it went from 20 kilogram meters per second to 4 kilogram meters per second. I lost 16 kilogram meters per second. Which begs the question, where did that go? If we lost it, we know it's conserved, it can't have gone anywhere. Well, the obvious answer is it went into the 8 kilogram box. So let's look just at this guy. how much momentum does the 8 kilogram box have all by itself? 8 kilogram box, 8 times 0, it has 0 kilogram meters per second. But after the collision, if I look at this guy, the momentum is 8 kilograms times its new velocity, also 2 meters per second. It has 16 kilogram meters per second. So what happened? It went from 0 up to 16. It gained, its change in momentum was plus 16 kilogram meters per second. So the change in momentum, 2 kilogram box lost 16 kilogram meters per second of momentum, 8 kilogram box gained 16 kilogram meters per second of momentum. The momentum was completely transferred. Whatever this guy lost, this guy gained. Overall, momentum is conserved, which is good because that satisfies our conservation requirement. In this case, if we wanted to then, we could take one more step and say we know that impulse, change in momentum, is force times time. If the change in momentum is the same in both cases, this guy gained 16 and this guy lost 16, then what's going to happen? One of them is going to have a positive force and one of them is going to have a negative force, which we kind of already knew. 2 pushes forward on 8, 8 pushes backwards on 2. So the forces are the same size but opposite direction, and the time of collision is the same. You can't have 2 pushing on 8 for a longer time than 8 pushes on 2, so the time's the same. So the impulse for both of these is the same. The force is the same. The time is the same. So how does that help us think about the acceleration? We have to go back to Newton's second law, F equals ma. In this case, for the 8 kilogram box, it has a big mass. If the force is the same in both cases, it has a big mass, which means it has a small acceleration. The 2 kilogram box has a small mass, which means it has a big acceleration to make the force be the same. So all of this ties back together to Newton's second law, which also helps us think about momentum transfer and accelerations and what the effects are going to be. So you might think, oh, the little thing hitting the big thing, there's a very small effect. The effect that you're noticing is the acceleration. The forces and the momentum transfer and the impulse and the time are the same for all of them. It's the acceleration differences that we notice that become important when you're doing collisions, for example, between small things and big things.